So I'm not gonna. I guess I won't hang around. So I think it's really great we're doing a department seminar. We've got the seminar back, and I think it's the first chance I've had to give a seminar in the department in a long time. And I think therefore it's a really great idea to focus on like a breadth of work that hopefully people will find interesting. And in particular, what I want to focus on is motion capture and animation research at camera. And I'm going to span like a range of activities. So the first thing I'm going to do is talk about what camera is for people who don't know. So camera was initially funded in 2015, around 10 million from 6 partners. The core of camera is to take what we might call intelligent, interactive, and visual technology, and to look at where we can apply it in different ways in the real world. And one of the themes is kind of creative science and technology, which is written there as movies, TV, and video games. And then we've got like health and rehabilitation, and another sub-theme area, which we call human performance enhancement. So I guess the crux of it is, you know, camera is interested in problems where you point a sensor at the world, you look to like interpret information from that sensor. It could be a camera, it could be like a speaker, it could be you know, it could be like some other kind of sensor. So you interpret that information, you try and understand it and make sense of that information, and then what camera does, we close the loop as well then. So we also we try and like reconstruct the world from that information as well. So there's a vision element. I would say there's like an AI element, and there's a you know, a computer graphics element really, and interestingly, like all the you know, there's so many problems around you know, industry and academia, which like, you know, you can apply this recipe to, which means we end up working with companies like the Imaginarium on, you know, motion capture research for films and games, or the Foundry, all the way to the NHS, where we're looking at, you know, predicting diseases, like disease behavior and stuff, all the way to the Ministry of Defence, so we're trying to do rehabilitation with service personnel, and then all the way to elite sport, right? So there's a massive amount of areas. So we've just got received more funding for 5 more years, and we have really interesting partners. We're going to be, you know, working with people like Sony, Epic Games. We're already working with, and again, you know, already, you know, back with the NHS and Ministry of Defence, and loads of interesting problems there. So my main interest in camera are, apart from, you know, apart from being director of the centre, which means that, you know, there's a high level strategic element to, you know, decisions in terms of what projects we work on and where we direct our funding. You know, I'm kind of like, I've come from this creative industries perspective, and that's generally what I'm going to talk about today. So just to say that there's, you know, every project in camera, at least that I work on, and I think I probably speak for most projects, there's a team involved, like, and nobody works really in isolation, or, you know, like that, you know, so even if there's a PhD student, like, so we know, so there are PhD students from RTI and PhD students from, you know, from CDE, and, you know, even if the student or the funding there originates from another project, they're still working in a team, which is maybe helping them, you know, 2 other people helping them collect data or process data, or sharing code, or doing something else. So everything is kind of like, you know, everything's collaborative, and everything's like multidisciplinary, and like, and everyone's cross-working, right? So there's not like a binary, this student in this box, kind of like this funding X, Y, and Z. Everything is kind of like spread around, and we share resources and knowledge and everything. And there are always multiple people on each project. And what I'm going to talk about today is essentially has involved a lot of collaborators, and I probably missed some people off there. If I have, like, you know, I'm going to immediately apologize, but I'm going to be, you know, I'm going to be talking about some of the work that I've done in the past, but also, you know, I'm going to be focused showing like amazing work which the team has been doing in like the teams that I would say that I'm leading. The outline of the talk. So 4 parts. Part 1, I'm going to talk about digital human research, and a focus on everything from animating faces from speech all the way to like puppeteering characters from performance capture. And then part 2, I'm going to talk about impact. So I'm going to start talking about how in camera we translate research into real world impact, and that's really worked well for us. And that involves our studio. And part 3, kind of then other interesting areas. So beyond humans, if you like. So we're looking there at things like animals and just arbitrary objects and things like hands and other things. And then at the end, then I'll talk about future thoughts and where I see where for me the research problems are. You know, what I'm going to be using to direct like my future research, like within camera. Start off with digital humans, and this is really interesting. It's been an area of interest for me since my PhD, and I graduated in 2006. And I've had the same slide for a long time in various forms. So digital humans. So you know, we're trying to create a digital representation of a human. You could look at, and it's a major challenge in computer graphics, and with applications in movies, and you know, lots of academic, like sticky academic problems. And I would say there are 3 different aspects. So one of them is the face or the character, or it needs to look realistic when it doesn't move. So the rendering needs to be really good. And then when the character moves, it needs to look really good. We've got dynamic realism. It needs to look right. And then it also needs to, you need to be able to relate to that character emotionally. And that doesn't necessarily involve realism, but there needs to be this emotional bond. So these are kind of like these kind of 3 challenges. And a lot of people just like kind of boil this down to the idea of, you know, in some shape or form, the Uncanny Valley, and which was a very, very short paper written by Masahiro Mori in 1970, and it applied to robotics essentially. But what he said was, as soon as you try and make something like a robot more realistic, initially the response to the robot, I'm not sure if you can see my mouse cursor, but you know.
Yes, we can.
Oh, great. So if the kind of robot was like a stuffed toy, then you might be empathetic towards that stuffed toy. You know, you might find it funny and, you know, cute. So you got the Pixar effect, I guess. And then as soon as you try and make that robot look more like a human, you start to get a response, which he called the Uncanny Valley. And then the idea was you need to cross this Uncanny Valley. And in computer graphics and film and everything, everyone throws this term around. Everyone talks about the Uncanny Valley as in terms of movies and films, and it's become this marker, become this kind of catch-all term for the fact that you're trying to create something like a digital human. Now, in reality, and this is kind of, you know, I guess like not a lot of people say this when they talk about the Uncanny Valley, but this is a fact, and it's my opinion. And basically, like the Uncanny Valley, it applies to robots, and it doesn't apply at all to you know, you can't recreate that curve in computer graphics, right? And people have tried, and it doesn't look like that. So there is no Uncanny Valley in computer graphics, but we'll use it as an interesting catch-all, right? Actually, I want to get back to that at the end. I'll kind of skip that. Like, you know, I'll skip a deeper discussion right now into that, but it's something I want to come back to later on. Now, if you look at the state of the art, and when I say the state of the art, I don't just mean academic. I mean, like, what can you do when you put unlimited resources into a problem, right? And the proxy for that is a movie or a AAA video game. So if you don't care about your budget, if you put 100 people working for 2 years on a problem and you give them a massive budget of millions, this is what you can do, right? So, like, you know, you've got 2016 Rogue One, and you've got 2019 things like Thanos, right? And this is an offline process. This is where you basically you have a problem where you're only actually essentially delivering like a few minutes of animation, right, for a film which may be like 2 hours or something. So you can like handcraft everything, right? You can fix problems by hand, and actually you're only doing a few minutes of animation, right? Like really, when you boil it down, it might even be 1 or 2 shots. It's like now another axis is when you look at real time and you look at video games. So this is where you want the performance to be created in real time, and why this applies more to video games is because then you're creating potentially hundreds of hours of animation, and you can't fix things by hand. So you want it to be right the first time. And they're 2 separate challenges, and they're starting to converge. But essentially, what you find is that everything is like what you find is that it doesn't matter which axis you look at. Everything is a one-off, right? Everything that gets created is created by a massive team. It's a one-off project. You can't just do something in a day. You know, you can't. The turnaround is really slow. And also, if you look at so there's an automation problem there. And the other problem is that the high watermark is still not real. So we're still not we still can't really create digital humans which are convincing. So there's still a gap there as well. So the other interesting angle is if you think about interactive characters. This is another application area. This is super interesting. So people have started to create, there's an area of research which is growing, which is called virtual beings. So here you might have, like this is an example from Magic Leap. So the person is obviously being composited into the video there, but this person with the Magic Leap glasses on is seeing this digital human and can interact with them. And the idea is that, you know, this is pretty scripted, right? But this digital human could potentially be autonomous, right? It could be a family, it could be a pet, it could be something else, right? And you know, with the explosion of things like, you know, transformer models and all this, you know, the GPT era, you know, the idea that you can kind of like, you can essentially procedurally synthesize interactions like dialogue, speech. This is a growing area. So the other thing which is really interesting is the idea of immersive worlds, right? So if you think about, and I put video games into this as well. So if you think about a video game like Red Dead Redemption 2, which you may or may not be aware of, but anyway, it's a AAA video game, so you know, flagship video game. It's expected to generate like, you know, 6 to 8 billion over, you know, 6 years or something. But if you look at the effort it required to make this game, right? So this game was 8 years in production, 1,200 actors, 500,000 lines of dialogue were recorded, and 1,600 staff, right? So that for me screams massive problem, right? Like a massive opportunity. So the problems which are of interest here are, how do you make this scalable? How do you make this process like the effort of 1 year, right, or 2 years? And where all your actors are maybe procedurally generated, where you need like, you know, 1/10 of the staff. How do you scale this up? And that involves, how do you create the assets? How do you create the worlds? And then how do you democratize it? How do you create tools then with like, you know, and think, you know, environments like Unity and Unreal, you know, a lot of people like, if you take, for example, one of their directions in Unreal is to actually, you know, add these generative models into things like Unreal, so you can generate characters and assets really quickly for games designers. So this is where the interesting questions are, right? Okay, so there's a kind of motivation, and now I'll get into some camera work. So bit of background from my background. So my PhD was in the area of trying to generate faces automatically from speech. So the idea is that you would take some audio, you would plug it into some model that you've learned, and this was a kind of like this is pre-neural networks, right? So these days you solve it with it's so easy to solve with a neural network. It's insane, but like this was super hard back in 2004. But this is like a non-neural network animation from speech. Be quiet. So, 'cause, 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 ' So it's not too bad. Like, I think if you stuck a neural render on top of that now, it'd actually look really good. It was a bit jittery, but the principle's the same. And then like, so that's an animation aspect. Another thing was then how you worked. I like working with psychologists, and we published a lot of work in what happens when you take faces and you manipulate them in some way, and you look at the response people have to that manipulation. So here we did a whole bunch of experiments where we would manipulate smiles, and then we would learn the parameters for trustworthy smiles and genuine smiles, and then we would put people in scenarios where they thought they were interacting with the real people, but it was actually an edited video of someone, and we could manipulate people based on how we manipulated the animation. So there's a correlation between like how you animate then and what someone's response is. And then we published in the past, using 4D facial capture, we've shown that we can, the effect of identity. So you can recognize someone just from the way they move their face, and you can use this as a biometric, right? And we did a lot of studies in that area, like 13 years ago now. That was. So that was all really cool. And so, like, one of the areas that I kind of did a lot of work in was active appearance models, which is a statistical model where you based on images, which you can use for, they're very popular for tracking faces. So then I actually started to work a little bit with double negative visual effects in London, and where they were making this film John Carter, and that was really interesting. And the problem there was they would wear these head cameras, and this was, everyone does this now, but this was like just after Avatar, so this was like only being used in anger in
Darren, we've lost your audio, I think.
Oh, hello.
Can you? Yeah, I think you're back.
Okay, sorry. I think I might have pressed the wrong volume button and muted myself. Okay, sorry about that. Am I still presenting? Yeah.
Yeah.
Okay.
Yeah.
Sorry about that. So, okay. So yeah, I'm not sure how much we missed, but I'm just kind of saying then, then I started working with DNEG on this facial motion capture problem, and the idea is that you track a face from a head camera system. This was applying like the work I'd done on facial tracking, and then you build a rig, and then you use that, and then you take the facial performance, and then you use that to animate, right, the creature, and then that's given to an artist, and an artist makes it look good, basically. But I was kind of interested in R&D and involved in this part of the project, and it's really interesting. So like, look, if you look at that problem, actually, like, people don't solve this problem these days. It's super hard. You've got all these soft, like the shadows, like you get complete saturation and clipping of like pixels. It's like pretty much impossible problem. So and so the only way to solve it is, again, in those conditions, was to have like the ability for an artist to go and fix things when they went wrong. So we ended up like R&Ding a framework which allows you to track the face under these conditions. But this is interesting. So, and it actually is still an open problem, right? Like face tracking, like to like a decent level is fairly solved, but face tracking to AAA visual effects quality level, you still can't do, like, there's still many unsolved problems in that area. Like, you can't train a generic system for like really high quality facial tracking. You still need to train systems which are specific to a person. So there aren't any one-shot solutions to this which give you VFX quality. And that's really interesting, the fact that problem is still there. So after this, this was again probably 2000, I can't remember what it was, 2007, 8, 9, started to, like, people were using 3D cameras to capture facial expressions. And actually in 2006 or 7, I commissioned actually the world's first 4D scanner from 3DMD. I asked them to build a 4D version of their 3D scanner, and they made the first commercial system for doing that, because we were interested in, taking the idea of, instead of analyzing faces in video, let's analyze the 3D movement over time. So this is a part of basically an example of a scan from a 4-dimensional scanner. So it's a 3D scan. I think this was doing it every 50 frames per second. So then what you can start to analyze and measure is how the 3D motion of the face. So you're getting this extra depth dimension. But this brings with it all these other problems. You can't use this kind of data in the same way as you use like image data. So you captured a really big data set of facial actions using this technology. There are about 10 people and about 500 or 600 scans, and this was the first data set of 4-dimensional movements published, which conformed with something called the facial action coding system, which is like the standard that people use to decode faces. And one of the things that we also had to deal with then was the fact that if you capture these meshes, you get a new mesh every 50th of a second. Every single mesh has got a different topology, right? And what you want is the same mesh topology tracked through the sequence. And if you know about meshes, if you just take a mesh and you try and track a mesh through a sequence of other meshes, it's a bit of an ill-posed problem, right? Because like if you take two surfaces, there's not really a solution to which to where the surfaces should match if you're basically sliding the surfaces on top of each other, right? You can measure the curvature, but but it doesn't mean that you're exactly corresponding where the mesh should match. But if you take advantage of the fact that you've got pixel and color information there, and then what you can use is you can use the color information to help tell you how to match the meshes, right? So what I did in this paper in ICCV was represent the geometry in 2D, and then to align to basically track the 3D meshes through time. The problem ended up becoming a registration problem. So you would basically have a sequence which looked like this in the top left of the meshes, and then you would try various algorithms to like align these meshes on top of each other. And then you would end up, so I ended up with this solution on the right here, which using active appearance models and thin plate spline warping. I'm going to skip ahead a bit. So this basically let us deal with this 4D data. Interestingly, I'm seeing this idea and this representation come back now because this representation is actually friendly for CNNs, where you've essentially got a 3D value instead of a pixel value instead of just a color value per pixel. You actually store the 3D value. And we've noticed some work where people are looking to apply CNNs on this kind of representation, which is interesting. And the actual data set that I captured back then has now become the basis for a model called Flame, released by Max Planck, and that's like become one of the standard models in face research in the vision and graphics community, which is interesting. So it's a really interesting problem, and it's still a lot of people still try and solve this problem in different ways. So I wouldn't say that there's actually a really like single press solution to this problem as well, of how you deal with this 4-dimensional data. This is a result, I think, of we ended up like taking all this kind of 4D data and building a statistical model of the face, and then this was the first kind of statistical model which was like this, and it let us then play around with the dimensionality of the faces and synthesize different faces. Okay, so just really quickly, one of the interesting things that you observe when you look at the face in 4D is also the fact that facial movement is non-linear from a geometric point of view. And the reason why this is important is if you take facial models, which are used today in industry, they're actually linear. So what I mean by that is every single expression in the model is when it's placed onto the model, when it's layered onto the model, the combination of the faces is done in a linear way. and the movement, like the smile, is morphed towards in a linear way as well. Whereas in fact, the face moves in a non-linear way when you form an expression. So here's an example. Here's a smile, and if you look at, this is a very crude diagram, but if you look at, I'm not sure if this shows up very well, but if you think about the way the face moves, the face actually moves, it doesn't move like this. This is what the model's doing. So this is what a state-of-the-art facial model will have in it. It'll have a linear blend shape, we call them. But what's happening now is the change in the face is happening all at the same time, right? Everything is moving at the same time towards this peak. Whereas in fact, what happens is, in a real, this is a 4D scan, this is a 4D approximation, then what actually happens is the face moves in different ways in different places. And this is interesting still even today, because when we capture 4-dimensional data for faces, one of the questions we still ask today is like, how do we best use that data in our model to make it more powerful? So we did a lot of psychology experiments with this, playing around with this idea. And what we actually found was, if you're building facial models, or if you analyze what's happening in the face, you actually find that some movements in the face are linear and some movements are not linear. And what this kind of then, what we ended up coming up with from this was a set of essentially some rules of thumb. And those rules of thumb would say, if you're modeling this part of the face, if you're animating this part of the face, put more work into it. You better have some non-linearity in there, maybe some physics or something. And if you're modeling like a different part of the face, so you've got a different facial expression, you should probably make that facial expression, you can probably use it, make it linear, right? So it ended up letting us come up with a bunch of rules of thumb. Okay. So this led on to as well another paper, and one of the, when we're dealing with this data, again, when we're trying to build these high quality models of faces, I think I've shown it's really important that you need to register all this 4-dimensional information, right? And the more accurately you can register, the higher quality your model will be. And there came a point where people were throwing so many cameras at this problem that they were starting to align things at the skin pore level. So you can see these kind of skin pores, and people were really interested in getting down to that deep level. So like this was around the same time that there's some work coming out in SIGGRAPH, where people were saying, oh, we can do this with optical flow, and that's a computer vision algorithm which like densely kind of maps pixels between they can map pixels between images and use that to do things like registration. And actually, like I actually at the same time was trying the same experiments, and I couldn't really get that to work. So I was like amazed that they were saying they could do it, but the secret was they just had so many cameras and so much data that they could make it work. And then interestingly, the next paper which that group published was saying, actually there's a problem with our last approach. It doesn't really work as well as we claim. Here's a super solution, right? Which generally happens, right, in computer graphics, which is super interesting, super fun, obviously. So I got interested in how you could do this dense alignment without loads of cameras. So this is a result of this algorithm we came up with, to really tightly aligns then these images as they change over time, and that equates to like really densely aligning all these meshes. So we came up with a new optical flow algorithm, and I'll skim over the details. So what we essentially did was we included a mesh inside the optical flow formulation, and this was the first time that anyone had done this. And what that mesh does is it gives you some structure. It gives you structure to the flow fields, because one of the things you find in optical flow is that it'll tell you like how to move pixels between a pair of images. But if you keep doing that over time, what happens is that these pixels end up kind of jumping across each other, and then you get these horrible kind of discontinuities in the face. So just jumping back, you'll see it here in this example, where you get this breaking up of the image. We wanted to keep the structure. We did that by adding this Laplacian mesh to the and Wenbin, who's now a lecturer with us and was my PhD student at the time, like put loads of work into this method, and we really really did a good job, and we came up with this great algorithm. And then you can use this if you've got some four-dimensional data. You can apply this kind of Laplacian mesh energy optical flow algorithm, and it'll register everything, and you can use it to register your faces. And these tables say that the algorithm was really good, according to the benchmark at the time. So I'll just skip that. So moving on. So okay, more towards the present day. So all this learning that we've done on faces, this started to lead to more projects with industry. So we started to do some work with the Imaginarium, and so here we're using more sophisticated assets, right? And we're starting to apply the same ideas. So here you've got an industry standard facial model, which you might use for animation. And so what happens here is that you've got all these controls, and if you move all these controls, you can kind of pose a face, right, in different ways. And you can also then change the identity. So the same set of facial controls to control the expression, you can map across to a different identity. So you can see that Ted's face, the controls, Ted's face are frozen, but the identity can be changed, and then you can make it look like Andy Serkis, or you can make it look like a pig or something else. So we worked with the Imaginarium, and we came up with a pipeline where you could take a 3D scan of someone's face and automatically build one of these models. And here's an example of one of the models we created from Sridhar, who was my PhD student at the time, who now works with Apple on the Apple X face technology. And then we're back to this idea, right, where you're wearing a camera. So we came up with a pipeline where you could then wear a head camera like this, like Andy Serkis is here. And we came up with a pipeline where you can capture the facial expression, the performance of the actor, and map it onto these little controls, right? So you can see these little controls moving, and then this gives us our facial performance. And if you want to, then of course you can morph Sridhar's face into a different creature, right? And you can kind of, that's how you do puppeteering of faces. So we spend a long time building this pipeline, right? And I'll skip over the details. And one of the innovations we came up with was instead of just using markers and measuring the 3D information from the face, we actually put painted patterns on people's faces as well. And we actually added an additional, computer vision elements to the approach, where we would classify what the facial expression was based on the configuration of the pattern, and we would use this to help decide what facial expression was happening at that time. And we found that was better than just using markers on its own. So if you actually paint patterns between the markers and actually take advantage of what you can see in the camera, you can come up with a better solution than just using 3D markers. We extended this work a lot further, and this is a two-dimensional version of the work, where you've got a video and then you solve a model. And what we found was, the headline for this work was, the models we were using about 140 blend shapes, or 150 blend shapes. And that was a lot more sophisticated than the work we saw that was being published, which was using about 30 or 40 blend shapes. So what I mean by blend shape is expressions, right? So the complexity of our models, because we were taking them from like a visual effects professional rigs, were a lot more than what we were seeing in academic publications. So we found that when you tried to track that 3D mesh in 2D, you'd end up getting a lot of artifacts in the tracking, and we were kind of scratching our heads going, why is this? People are claiming this is not a problem. But it was because of our complexity. So we ended up coming up with an additional prior distribution, which we learned from pre-existing motion capture data we've captured, and we solved this problem, which fixes these depth ambiguities. I'll skip this part about rendering. Okay, so there's a bit of an evolution of work, right? So that evolution of work is all the way from when I started, I guess, being interested in faces, and trying to build a team and build up camera. So Camera One was funded then about this time, right? About where I'm going to start from now. So we'd already done a lot of R&D, and then so what we decided to do then, what I decided to do in Camera was try and put together like a commercial element to what we did in Camera. so that we could take this research on faces and motion capture and use it in commercial projects and create impact. And that's what we did. So we have a studio in camera, and we've just setting up a new studio in Bristol. So we're expanding like this outreach into industry, right? And if people want to see the studio, it's it's a bit tough now because of coronavirus, but like when that starts to become easier, maybe we could start to we can start to like be a bit more open, and people can come and have a bit of a tour, see what we do. So I'm going to talk about some of the commercial projects, and these projects are delivered by there's a lot of people who've come in already, been in camera and left and contributed to these projects, and they've now gone on to great things. And there are some people who gladly are with us, like still. And Martin Parsons is our head of studio, and him and the team there have contributed a hell of a lot to these projects. So one project we did was with Magnification, and this was the first project where we used we had this internal code system where we could take take our 3D scan and automatically build a facial model. So what we did was we delivered about 5 facial models. We were sent raw scans of people from Mexico, and we would build these facial models really quickly, and we would send them back to the company, and they were on location in Mexico. So we used our technology for doing like non-rigid registration of meshes and deformation transfer to deliver that project. Another project we did was with the BBC and Aardman Animation, and there what we did was we took like this, all this academic work that we'd done on building facial models and doing motion capture. Like we kind of like had to engineer this really, like all the work went into like engineering this pipeline, which let us do things commercially with it. And we ended up delivering face and body animation for this immersive experience, which you can download from Steam with the BBC. So we had an actress, an actor in the studio, and you can see we're analyzing the face. We built the facial model of her. We delivered all the motion capture and all the facial performance. Another project we did was with a company called Satore Studios, and now what you can see is that we've started to extend to bodies. So now we're taking a scan of a body, and where we've got this pipeline which takes the body scan and turns it into a rig which you can use to create body animation. And the team right now are working really hard on trying to get this process really created quickly, because one of the things we're interested in is real time creating digital replicas of people and then doing real time studies in VR, right, and AR with these models. So we created this whole experience, an animation of face and body, and this one, like this has won quite a few awards. This project. We also delivered for Aardman's video game 1111 in our studio, and the team worked really hard to do this. And we've worked with Welsh National Opera and a company called Rewind on a virtual opera performance. So you can read about this on our website. These projects you can read about on our website, on our news and commercial pages. There's some really innovative solutions for doing motion capture with football nets. Okay, so we've also got other things which have happened since then. We worked on the Innovate UK project where we've been trying to work on animating faces and bodies from video, from camera studio. So kind of trying to rely on video solutions for faces as opposed to markers. We've worked on some interesting problems where, one of the problems you find a lot in motion capture is, and this is Mariam. So Nadia's been working on this Harpsy project, or was working on it, and Mariam was working on this retargeting problem. And one of the things you find is that if you get 2 actors and they perform an action together, typically what happens is the character they animate is generally a lot bigger or not exactly the same body size as them. So when you translate the actions across, then you find that, in this case, the high five doesn't match, right? So Mariam's come up with some really awesome solutions to this problem where you can retarget, you can fix these contacts, right? So this has essentially been her PhD research. And this is like really the tip of the iceberg, this problem as well, right? This problem is, it's one of the main problems, this retargeting of body contacts. Is one of the main problems you find you have to fix by hand when you work with motion capture data. So this is like, I think, the tip of the iceberg to this kind of research. So one of the problems I'm just going to quickly focus on is this work we did where we were developing, again, how do you create animation like really quickly and at a high level? So we came up with a solution which uses evolutionary algorithms. So the idea is that you can find a good bit of the video. So if you want to create the face, and you can see this face going crazy right on the screen. But if you want to create pose faces and create facial animation at a high quality, you need a lot of experts. You need a lot of expertise. So the idea was we've got this MRC funded project with UCL and with Imperial and with Queen Mary University London. And the idea is we want to come up with a platform which lets you create faces at a high quality, but anyone can do it, like a child can do it. We've actually got children using the system. So we come up with a system where if you look at a face, like a facial animation system, if you play around in the parameter space of that facial system, you can what happens is like you can this kind of thing happens. You're changing the parameters randomly, you're exploring the space of potential faces. So somewhere in that space is the face you want, right? So what we came up with is an evolutionary strategy for finding the face you want. So using evolutionary algorithms, right? So genetic algorithms. So if you know about these algorithms, the way they work is you're presented with the different generations of things, and you make selections from that generation, and they become like the fittest samples, and then you evolve another generation. And the idea was someone would be able to select faces from an interface, and they'd select faces which look a little bit like the face they want. And then as you went through these different evolutions of the face, you'd end up with finally the face that was in your head, right? So you're minimizing this difference between the face you can see in your head and the face you can see on the screen, right? So this is kind of what it's like. So so you're presented with all these, so you're thinking to yourself, what does fear look like to me, right? So you're presented with a bunch of faces, and then you make some selections of the faces, and then from these seeds, more faces are evolved, and then the system shows you more faces. You make some more selections, and then eventually you get to the face, and you're like, that's the face I want, right? So it's a really nice way of generating the faces. So we've used this system already in a whole bunch of experiments. We've actually and there's a whole bunch of papers under review. And we've shown that you can actually use the system, and it's pretty effective. We've got an experiment where we've got over 100 people have used the system, and we've got statistics and evidence which shows that you can converge these groupings. People will converge to different groupings. And one of the whole ideas of this project actually is what we want to do is we want to look at different psychiatric groups, right? So we're looking at people with autism or people with depression or people, schizophrenia. And what we're trying to do is understand how they interpret faces. The general way of doing this right now is you'd ask people to describe faces or select, the methods are not very sophisticated. But the method we've got where we ask, we say, what does happy look like? And we get these different groups to, hundreds of people in the schizophrenic group, to generate happy faces. We'll end up finding on a facial manifold, what their face group looks like. And then we can find out what a normal population look like, let's say normal, or what another group of people looks like. And we can start to learn then what the mental models of people's faces look like. And that's the whole idea of this project, is to look at all these different populations and try and understand how they interpret facial expressions. Okay, just kind of coming, like, slowly coming towards the kind of end. Obviously, we wouldn't be a motion capture group if we didn't look at bodies as well, right? So we're interested in bodies. We're more interested in when we're building more activity in this area. And there's a massive bunch of work in the computer vision community now on graphics, on capturing bodies, and it's crazy. It's like super competitive, and like every conference there's a new algorithm, and people are getting better and better. But one of the things we do in camera, I said, was we work with sports and we work with healthcare. So what we need is, we don't just need the ability to fit a 3D model to a body from a camera for for virtual try-on, for like shopping or something. We need it to be really accurate for elite sports performance and for biomechanics, right? And what we found is that so we've captured a data set actually of like a gold standard biomechanics data set of body actions, and we're evaluating all these different computer vision algorithms, all these different techniques, and we're finding that they're not as accurate as the gold standards, right? And they've got all these flaws. Give you an example. Here's an elite sprinter running through a motion capture volume, and you can see, like, something off the shelf. That might be open pose, it might be some other algorithm. They don't generally work that well. So and the problems we're interested in are these kind of problems, right? We want to do elite performance capture of these people, but without motion capture system. And this is the British Skeleton launch track. I don't think this is the one at Bath actually, but it might be. So actually, what we've done is we've built a computer vision system, which we make a tunnel of these cameras, and we put them along the side of the track, and we've started to actually we're working with the British Skeleton team, and we're actually already giving them insights into their training and insights into their sprinting that they haven't been able to do before. And the good thing is that our system can be used in the wild. So we're going to be taking our system onto ice track training, and the skeleton team are going to be using it for ahead of their preparation for the next Winter Olympics. So we're really already making an impact with this kind of high value, high accuracy capture in elite sport. And in camera too, we're going to be working with other sports partners, Lawn Tennis Association, British Athletics, and we're going to be rolling out the system. To give you an idea of one of the things it does, like, this is the indoor sprint track at Bath, and you can see our old version of the system where we used big 4K cameras, and it can tell you things like, where did my feet touch the ground, and and then and we showed that we compared this to a ground truth of force plates on the ground, right, where actually someone makes a physical contact, and we've shown that we're pretty much as accurate as the force plate. So we can get as accurate as like mechanical measurements with cameras. And when you've got this information, then you can get information about your stride, your step length, the frequency of your stride, and then you can start to measure this information. We've also come up with multi-view camera systems. Apologies if this is a bit jittery, but we can fuse different algorithms from different camera views as well, and we can come up with more accurate tracking. We're currently doing this big evaluation of different computer vision algorithms on this problem. So in the future talk, maybe Murray or someone or Laurie can, I think it'd be great for the department to hear really in depth about all this work that we've done. Okay, so last part, I think I've got enough time. I think I've got until 1:15, right? It's about 10 minutes. So I've talked a lot about faces, and hopefully you can see that there's been some, lots of applications that we're interested in. But the world isn't just about human bodies, human faces, and also from a research point of view, you need to pick your problems sometimes, right? I think there's so much work which has gone into in the last 5-10 years, like especially the last 5 years, on modeling faces. There's so much money, so much resource, and the same thing with bodies. Because industry is interested in these problems now. So there's massive, like, you can't keep up with these advances. So we started to get interested in animals, but animals are kind of more interesting than humans in some way, because like there's not that much variation actually between people when you compare it to the animal kingdom. Even if you compare different breeds of dogs, right? I think there's more variation than humans. And then that's just one animal, right? And then if you look at pigs, or you look at horses, or you look at birds, and there, and if you compare the data which people have on human bodies and faces compared to the data we have on animals, we are like, and the modality of the data, we are nowhere near close, right? So there's a massive gap in like obtaining high quality animal data, and that's what one of the focuses of camera is right now. To give you an example of like some animal data we captured, here's a pig, and here's a dog, and this is Maggie, who's sadly now left us, but she was our mascot for a long time. We started working on animals because we were working with the Imaginarium on a project where we were trying to animate animals from actors, right? So the actor would act like an animal on stage, and then they would try and turn this into an animal performance, because they were making this Animal Farm movie, and they didn't essentially have any motion capture of animals. So we captured this pig for them, and that was literally, all they had. And we were going to capture, but then we were going to capture more animals, but as what happens in the film world, the funding got pulled. Actually, the Imaginarium went into administration. Now they've recovered, but they're not quite the same company. They're a bit different. So that project didn't really, that film ended up not getting made. But we were interested in animals. We saw the potential. So then we started collecting those of dogs. So we collected about 16 dogs, right? Because we're right next door to this cats and dogs home in Bar. So we would the dogs would get walked over, and the team, a massive, the Mocap team in camera is like really big, and it took everyone, I think, to like a massive logistic effort of getting the dogs marked up, and even now, like, we're still processing data, right? But we ended up capturing this big data set, a motion capture and 3D data set of these dogs. And then Sinead, who's was a PhD student and is now with us on the Mocap team, took this data and then built this really awesome model of dogs, which is used now on a few different projects across the center. And she came up with the first Connect, like, RGBD device for doing animal motion capture, basically a quadruped capture. So you essentially point a Connect at a dog, and then it gives you a skeleton and also gives you the shape of the dog. And we published this as CVPR, as well as some of the data which was associated with that. So this is awesome work, and it's only scratching the surface of the potential of the data that we've got. We've got other projects ongoing on like animal style, like how you change style. And George Fletcher's working on that project, and also Joyce, and and then we've got Jake, who's working on kind of the machine learning approaches to like extracting information from video of animals. And one of the great things that came out of this project, also one of the great results that Sinead came up with, was actually the algorithm works on depth information from like animals like of different breeds as well, like to some extent. So if you take like a 3D model of a panther, it'll still give you the skeleton of it and actually like try and approximate the mesh. Like, obviously we didn't have any panthers in our 3D model, right? So we didn't get this, it didn't quite give you the shape of the panther, but it gives you, I'd say, like a pretty good approximation. Okay, so last technical slide. So also we've got like a really great project. We've got a CDE student, Catherine Taylor, who is, again, has been working with a company called Marshmallow Laser Feast on kind of technology which lets you interact with objects, real world objects, in virtual reality. And this actually started as an Innovate UK project. So again, there's been a big team behind this for a while. So we had Pedro, and we had Murray, And then Catherine was working on algorithms which let you, use like an RGBD sensor, or kind of this motion capture volume we created, and it can track objects in real time, and then put those objects into that virtual environment. And then recently with the camera team, with a wider team like Eleanor and Martin and a bunch of other people, we've captured this like really big data set of a ground truth data set of like egocentric RGBD capture and objects and motion capture, which we're now writing up and we're going to submitting soon and releasing. So there's been some really great work in that area. So I think I'm going to be on time, which is amazing. So just to kind of wrap up then, I've given like a big overview of different topics. And obviously, I've not solved the problem in this talk of like how you fix scalability and how you cross the Uncanny Valley and all these different problems, because this is going to be the result of the entire probably working for the next 20 years, right? So there's a lot of work still to be done, right, in this space. Like it's by no means solved. So therefore, looking at future directions, what I think is interesting, and what I think, like for my group and for my part of camera, I think some interesting problems are more. So looking at the first problem, like how do you make the Mocap pipeline more efficient and easier to work with from capture to animation for faces, bodies, humans, and animals? So, it's still, when you use motion capture, you come up with the same problems all the time, like cleaning up data, fixing retargeting, problems, however they might look, right? And it doesn't matter if you look in the academic, there's some work just recently in the academic literature which is starting to become aware of these problems, but like from a practical point of view, like these problems are real and they're still not solved. You still need people to fix things by hand, like 90% of the time. Another problem is like to do with performance retargeting. Like, how do you transfer the intent from a performer to a puppet while being faithful to the physiology of the puppet as well as the identity and intent of the performance? So what I mean by that is, if you're a human and you're meant to be like, you're going to be motion captured and then you're going to be animating like a horse or a dog or an ape or something, the actor's performance is taken and then transferred to that animal. It could be a dog or something. There was the Call of the Wild movie recently where an actor was essentially roto-animated into a dog. But that doesn't move like a dog. It doesn't move like the animal. But it's still a physiological gap, right? Because of the physiological difference between the actor and the puppet. So how do you close that gap, and how do you maintain also the without losing the essence of that performance? Another problem is how do you create like animatable models and know how they should move from a limited amount of data. So let's say I modeled a creature like a dragon. I want to know then how that's going to move. I want to know like how it moves in the right way, right? Like in what style should that move? In the same way as if I create a facial model, how should it move? Like and I think that's like a one-shot, few-shot kind of problem, right? If you want to look at it that way in terms of AI. So I could take Mike's face, right? And if I just look at Mike's face, I can probably guess how he's going to smile, right? But that's still really hard to do from a vision point of view. I can just guess by looking at one image of his face where he's smiling now. But I can probably just guess how he's going to smile. And I can probably guess like all the expressions he could make, if you ask me. And again, like that's a really interesting problem from an animation artist point of view. If I could just like sculpt something and know how it would move, right? And also, like going back to the Red Dead Redemption problem, how do you make this process of high quality animation performances, cutscene generation, storyline generation, how do you make all that scalable and automated? So there's a whole procedural like problem there, right? Like how do you procedurally create all these different things? And I think a lot of the AI research, the transformer research, the text to speech, translation of voices, all this kind of research is an amazing foundation for that, right? And again, like that's only begun, that research really, like so there's again there's 20 years of research there. And just to kind of wrap up, I would say that how do you cross the Uncanny Valley, and I'm going to call it Maury's Uncanny Valley, and then also how do you push animation that is already amazing over the line to give you that 1% of realism, right? To give you that last tiny bit, right? Like when you've already done the best job you can and you spend hundreds of millions to make something realistic and it still doesn't quite look right, how do you cross that threshold? And I'm going to give you two final thoughts on that. So the first one, I said, how do you cross Maury's Uncanny Valley, right? Because I think there's a difference between what people say when they say the Uncanny Valley in a broad sense, you know, it's realistic, versus what Maury meant by the Uncanny Valley. So if you read Maury's paper, when he talks about the Uncanny Valley, he's talking about robotics. And what he actually means by uncanny and creepy is the fact that when you're in a room with a physical robot which is trying to be human, it feels creepy. So if you've ever been to like a waxwork museum, that's the closest analogy, right? If you're alone with a waxwork, it's creepy, right? And that's different from if you're watching a face on the screen. And the difference is that I think what Maury means really is that to cross the Uncanny Valley, you need to feel like you're in the same room with something, right? That's what I think Maury's Uncanny Valley means. I think it means that to cross the Uncanny Valley from Maury's point of view means that you feel like you're in, like there's a synthetic human that you feel like you're in the room with, right? So I think that's really interesting. And I think therefore it's really interesting to think about augmented reality. So I think augmented reality then is the closest, like, you know, we're years away from this, but it's the closest comparison. So you put the HoloLens on, and then you see a digital human, and it feels so real. You see like your mother who's like 100 miles away, and you're trying to and you like this kind of holopitation application, and you feel like you're there with that person. So that will be for me crossing Maury's Uncanny Valley. So that's interesting. And the last thing I talked about the 1%. How do you get that last 1%? So this is interesting. So this is my last slide. So if you saw the new Blade Runner movie, then you would have seen the digital Rachel which got created. So on the right you've got a digital recreation of Rachel, and on the left you've got the original movie frame. And there's a scene in that film where they have a digital version of Rachel because she's obviously like in her 50s now, and at the time she was in her 20s, right? So they try to make this character, like they took another actress and they try to make her look like Rachel did in the original Blade Runner movie. And like it still doesn't look quite right. There's still something not quite right. And I was talking to the visual effects supervisor on the movie, and they said the same thing. And it's like, because the problem is too complex, there's too much going on in the face, right? There's too many things, there's too many parameters, there's too much stuff. And I think this actually relates really strongly to this idea of, if you've ever seen this work from SIGGRAPH back in the olden days of 2013, before neural networks, then like there's this idea of motion magnification. So if you take a video like on the left and you actually magnify the motion, you see a lot of stuff going on. So that video on the left, if you try to animate that eye by hand, right? Like you'd be like, how the hell do I animate it? Because you know, like there is stuff going on, but how would you animate it? And if you look at the video on the right, you can see all the motion that's happening there. So that motion is present right in the video on the left, but it's kind of like at a subconscious level. It's so fast, your brain is not registering it, right? So there is all this kind of like underpinning biological. There are all these biological signals, right, going on underneath. There's like kind of biomechanical, biological layer, which needs to be added to the animation, and so that's my hypothesis. So I think you'll be exploring how you add these kind of biosignals back into the synthetic videos, and I think one thing which I think this is on the right track, right? If you look at the state-of-the-art work now for detecting deepfakes, which was just published in PAMI, they actually detect deepfakes by looking for biomarkers, and they use this algorithm actually to extract features like heart rate. And so I think this is on the right track. So basically adding these synthetic layers, I think, is the way to, could be the way of crossing like the movie Uncanny Valley, if you like. Okay, so I just once again, thanks to like all the work I've talked about is, you know, massive team effort. So I want to thank the team. And that's the end of my talk.
Fantastic. Brilliant. We are a little bit over time, as Darren said, but anyone who's able to stick around, Darren, if you've got sort of 10, 15 minutes to stick around, could we do some questions?
Yep.
Cool. So put your hand up if you have one. I've got at least 3, but I'm not going to take chair's privilege straight away. So anyone like to ask a question? Willem.
Hi, I think I'm unmuted. Thanks, Darren. That was really nice. So I've always been intrigued by this Uncanny Valley thing, right? And I think a lot of people have been. So you say it's different in graphics than it is in robotics, and I can believe that. But there are similar things going on. So when I read about the Uncanny Valley previously, long time ago, I thought it had to do with sort of an instant repulsion you have with what you're confronted with, and this has happened recently, very recently, with things like the movie version of Cats, the new Lion King, the new Jungle Book, all those where they try to put human faces on animals that are sort of too realistic. So do you think is that kind of the same thing? Is that related to the graphics version of the Uncanny Valley?
Well, this is just my theory, right? And it's probably against what normally what people would say about what they understand the Uncanny Valley to be. But I firmly believed it for a long time. Like I think there's a different feeling between being creepy, because I think what Maury said was creepy, right? It's not repulsion, it's creepiness, right? It's like the uncanny, like translation. People have actually analyzed what that word means as well in terms of this. But I think it was for me, there's definitely a feeling between like being physically with something which is trying to be real, which I think which Maury could only have meant that, right? Because at the time there was no CG, no games, nothing like it at all. It was completely about here's a mannequin, here's a robot which is trying to be real. And I think like maybe there's something different in CG, but I'm not sure if it looks like a valley. And I feel like for the last 15 years, people have been trying to shoehorn this Uncanny Valley and like justify it in computer graphics term. And it's kind of stuck because it's a good term, right? And it sounds good. And like, yeah, why not use it to describe, like, yeah, fine. Like, why not use it to describe like trying to make something look CG and look real stuff? So that's completely fine. But I think there's also Maury's Uncanny Valley. There's maybe like another version of it which is maybe slightly different. So maybe that's what I'm thinking is, if you could replicate the creepiness in augmented reality, I think you can kind of do it in virtual reality. Like if you've ever tried like interacting with humans in virtual reality, like digital humans, you get closer to what I mean. Like you get fear, like real physical fear, not like there's a difference between looking at cats and going, that looks a bit weird, that looks a bit weird, between being physically scared, which you can get in VR from a digital character, and that's the real then you think, okay, that's different from thinking that the eyes in the Polar Express looked like zombies, which I think is like stretching it. That for me has always been stretching it, like it. So I think that's my kind of take on it a bit.
Well, that makes sense in the way that very few people will have the actual experience, right? Of an uncanny robot that they are in a room with. That will be extremely rare, and a lot of people have seen these animations that are not quite right, and they're like, so it could be that, it could be projection, but the effect of being creeped out by, or just having a severely hurting eyes by these modern things, is that studied in the same way? Does that have graphs where you can see what happens?
Yeah, and they do that.
Right, but where do Cats and the Lion King and the Jungle Book fit on that?
I'm not sure if anyone's done it with Cats, but the last studies I saw in this area where there is no valley, it's basically like as you make it look more real, it starts to look more real. Like, yeah. But the Cats thing is different, right? Because also you could argue that the Cats thing is not trying to be human, so it also falls into this it's maybe a bit of again an anomaly. Maybe there's actually another axis somewhere.
Yeah, that's exactly what I'm getting at. What's the space here, and what's the origin? Anyway, I won't take up more time, but thanks for that.
No, it's an interesting discussion, and actually, like, I'm tempted to write a bit of a paper on it, and I'm assuming it's going to get like people going, "What you're talking about the uncanny?" You know, it's because it's popular culture right now. But I think but like scientifically, like Maury's paper was never scientific, right? It's like a one-page paper with no data. Like here's a sketch. I think things look like this. Like it's a hypothesis, and actually nobody's proved that hypothesis yet with CG or games or graphics or anything. So like nobody's like the data doesn't fit that model, right? But I think like I'd like to, but nobody's explored this in augmented reality, and I think if you did that, you might find that it starts to look more like that valley. I think that would be the thing to try, something like that.
Cool, very interesting.
Thank you, Matthew.
Hi, sorry, this might be a really nerdy question, but when you're kind of representing some sort of emotion in, you're basically transferring like one emotion from one thing to another. How many data points are you actually pushing across? Obviously, I can look at a 4K video and I can say, it's that many, there's that many points of, there's that many, much data which is being streamed at that time. How many points of data are actually being transferred across to currently to actually get that emotion onto that kind of puppeteered face or body or whatever else?
Well, if it's like a 3D, if your underlying model is like for the face, if it's like a blend shape model, then it'll be the number of blend shapes in the model, which could be 1,000. It could be 50. It could be 100. It depends on a lot of different things. So like for a movie, it would be the order of 1,000 or 1,000 plus, and then maybe it would be more in the order of hundreds for a game, or maybe if your bandwidth was lower or your computing power was low, might be if you wanted to do it real time, it might be lower again. But yeah, there's definitely there's probably an information gap between like what a real person's doing in the face, right, and I think what's currently encoded. But I think that's part of the challenge, right? It's how you close that gap, because currently, like, to make these blend shapes and make these controls, it's kind of like a manual job, right? You give it to an artist, or you give it to someone who's really highly skilled, or you scan someone's face with a 3D scanner, and then you try and squeeze that into your model in some way. So there's like a lot of manual work there, and this is where I think that there's a neural rendering, like a neural animation element of this. Like you should really be able to, like, with enough data, maybe be able to learn to like procedurally add that layer on that. I think that's like what you, I guess, should be able to. That's where I think it gets interesting, but it's currently very small on the 3D sense. Obviously, in the pixel, there's the face of space is a lot smaller than the space of like the dimensionality of like a 4K image or something. Or that's what people say. And for bodies, then it's usually based on the number of joints in the skeleton and then some other parameters, again in the order of hundreds or whatever or less, to describe the body shape.
Excellent, thank you.
James?
Hey, just one question about ethics, really. I mean, with the software, you're making it to the point where a child can, do your animations and, get to the point where you could create a real human animation. Do you think there's ethical implications in terms of deep fakes and, anyone being able to generate a deep fake? And is there any way of stopping the nefarious side effects of what you're doing at the moment?
So I think right now there are no nefarious side effects to our tool, because we're not good. It's not at the deepfake. It's like our current tool is like 3D video game kind of style, right? But yes, we're actually trying to add a neural rendering aspect to it, so what you create is photorealistic. So, like, currently our tool like only creates still images, really. So you can create an expression, and also we don't have any plans for it to create animation. So you wouldn't be able to use that tool to like make someone say something that they wouldn't say, right? So so I think there's two different things, right? There's our project and how it applies to this, and then there's the broader discussion, right, about deepfakes and around like making sure that they're used ethically, I guess. Like, so in our case, we don't assume that we're going to be approaching this. Everything is supervised, right? Anyway, right? So the use of our tool is supervised with child psychologists and ethical studies, and people like a child is not allowed. It's like you can't create someone, and do this kind of and do this kind of thing, and the space of the faces wouldn't let you do it anyway because it's we've got these constraints. But like there's obviously a broader conversation around deepfakes, and unfortunately that's not going anywhere, and actually it's going to get better. And like right now you can actually, the best deepfake detectors are pretty good at detecting deepfakes, but yeah, this is a problem, right? And it's going to be bodies, and it's going to be like complete fabrication. People are not going to stop trying to make things better. So how do you solve this problem? And like, you either solve this problem by coming up with solutions which try and authenticate like the provenance of the video, like, is it real or is it fake? Like, can I look at biosigns? Can I do other things? But that's really hard to do, and maybe there won't be a solution to that. So I think some people have proposed other solutions. So I've got a colleague, John Colomus of Surrey, who's got just got a centre funded equivalent to Camera. Actually, it's looking at how you use AI, like privacy technology, like security technology, in a range of problems, right? So he's worked with the National Archives on blockchain and provenance of things, right? So maybe one thing is like we need to start like using maybe technologies like blockchain, or on when there's ever official video of people, like say the president or something like this, like there needs to be some authentication on that video, like that. So when it's like so there's provenance, so there's maybe blockchain, so where it's come from, if it's been manipulated, if it's been changed. So I think maybe like instead of looking at computer vision detectors, maybe I think we need to come up with an infrastructure solution around like video, which we think is going to be like people who are public, like the creation of video, maybe that needs to be curated. I understand that's got its own difficulties, but I think we're just going to be faced with those challenges as for a long time.
Good stuff.
That's great, thank you.
So I have a question, Darren. So it's kind of going back to Willem's question, really, and also about the deep fakes in some ways. And you use the words at the end of the talk, the essence of a performance, right? And I think it's a really nice phrase for what sort of the artists or creative people you're working with would say about creativity. Like there's some essence to it. And I think if you talk to a musician, a virtuoso musician, or an actor who's really kind of accomplished at their craft, they will talk about getting into a character and really sort of and they will be able to look at their own colleagues and peers and say this person's a better actor than that person, right? So there are real nuances in all of that stuff. Similarly, listening to a Beatles cover band is never going to be the same as watching John Lennon sing, right? Despite the fact they're playing the same notes on the same instruments in the same order. So there's this kind of really subtle kind of gap, right, between the real thing and the fake. And I really liked the thing that you said at the end about the kind of phase-based approach, right, where you're kind of amplifying these kind of micro movements. So really, my question is, I think that's a really nice kind of way of thinking about that gap between the kind of the authentic and the fake. And my question is kind of almost like a philosophical question about whether you think that approach, the phase-based approach, or some other kind of approach like it, could ever really get you to something that was authentic, or whether authenticity will always have some kind of ephemeral quality which can't be captured just by movement or by recreation in some way.
Yeah, like so I think definitely there's a biomarker, like bio thing which is currently missing, right? When you're trying to create stuff, like so, it's a conversations with a guy called Mark Sagar, who was at Weta and who put together the avatar pipeline, all the Weta pipeline on facial performance capture and all this kind of stuff. So he put together all these pipelines like 10 years ago, and even 10 years ago he said, I was talking to him and he said, like, you know, the thing that's missing is the fact that these digital characters, like a real human, as a nervous system, like they have like, you know, and our models don't, like they have all these things which happen to them, which, and you know, so his thing, and then he ended up leaving Weta and he's a professor at the University of Auckland, and he set up this laboratory of animate technologies, and he kind of tried to like replicate his son, this digital version of his son, and he kind of 3D he took all this VFX technology and like he created this thing called Baby X, and he created a startup called Soul Machines, right? And his philosophy was you try and build a digital human from the ground up, you try and build a nervous system, and you try and build and I think he's right. Like I think like, you know, we have none of that in the CG models, right? None of this in the models we have now. So, you know, we do everything from a shell basis. We do everything from the outside in, right? So I think we are missing that. So that's the first thing. And I think like one theory is like you know, hypothesis for an experiment would be let's add it in some way and then see if it's better, right? So I think it would give you something, but then I think on the other hand, you're talking about this maybe something like called style in some way, like you know, so there is a loss between, like, so Andy Serkis used to say as well, like, you know, one of the things the Imaginarium was he wanted to capture the essence of an actor, but one of the criticisms at Weta and all these companies was, you know, Andy Serkis's performance was created by the art, like Gollum's performance was actually created by the artist and not by Andy Serkis, right? And he didn't like to say that, so there's actually a big tension between the artists and the actors. And Andy Serkis, like, it's about what goes on in the actor, but then the animators would be like, I'm pretty sure I animated that, you know, and like so the technology still can't extract that, right? In some ways, but I think like the closest thing I would say, right, is that there's a bunch of work right now like on style, and coming from the computer vision domain, and maybe non-photorealistic rendering, where you take a photograph and you try and make it into the style of something else, right? And that's across to computer animation. So actually Christian had a paper with some people where they were looking at how you transfer, like if I animate your face now, like it's going to be in my style and not yours, but if I've got a bit of an idea of what you move like, I can inject your style, right? So there's the idea of cycle loss in neural networks came in through the computer vision community, and that started to come into the motion capture community with a paper from this year where people are like, you know, like how do you learn the style from an example of something and inject it back in? So maybe there's a combination of things, like, so like there's a style element, there's a bio element, like, you know, the way I move and gesture is different from yours, different from, so we need to look at it at different levels. So there's a medium level of detail, which is like the way we broadly gesture and the way we broadly do things, and then there's a micro level which may be a bit more regular, like I don't know, just the fact that like my breathing, you know, and other things. So I think there's probably different solutions at different levels, maybe. But yeah, it's a really interesting area.
Brilliant. Thank you so much. Matthew, is your hand still up or up again? Just to check.
No, it's I didn't have my hand up again. Sorry.
Okay, no problem. Brilliant. So if you could join me in thanking Darren again, that was absolutely fascinating. Thanks, Darren.
Well done. Right. Thanks, everyone.
Brilliant. Thanks, mate. Great, that was wonderful. What a great seminar. And I'm not sure who we have next time. I really should know.
Professor Peter Hall.
Peter Hall will be coming and talking to us next time. So do come along for that. I'm sure it will be fascinating. Brilliant. Thanks, everybody.
Thank you, everyone. Have a good day.
Bye.